Hello everyone and welcome to the fourth lecture of Digital Elevation Models and Application course. In this particular topic we will be discussing again various techniques to generate digital elevation model. This is part 3 of this one and last part of this techniques for generating. One more technique which I would like to discuss, though it generates only at a coarser resolution, but the advantage is that the data is available free. It can be generated. As we have seen that we can generate from using survey topo-sheets, using ground information. We can also generate stereo pairs. We can also generate through using radar or INSAR technology. We can also generate using LIDAR technique. Thus, in this particular one, we will be briefly discussing how thermal infrared data can also be used to generate digital elevation model. See, this is a general concept that the temperature and elevations are inversely related. And this relationship, inverse relationship has been exploited, and this can only work where you are having natural, undisturbed or less disturbed terrain, and especially if we employ the nighttime data, as in this example, we can generate digital elevation models. But here the example which I am going to show you has generated digital elevation model at 1 kilometer resolution, that is at 1000 meter. But nowadays this thermal data is available at 60 meter resolution from Landsat OLI series, and therefore we can also generate digital elevation model employing nighttime Landsat data at 60 meter resolution. Because one can argue that since I am having a 30 meter already available digital elevation model, so why I should go for 60 meter resolution or 1 kilometer resolution? See, the no digital elevation is perfect. So we have to keep trying different techniques for our utilization. Sometimes a very high resolution digital elevation model is not required, and then if you downgrade it, you might create some problems. But if you employ already a generated digital elevation model at that particular resolution which is required for your work, then it is good. So in this example, we have used the NOAA AVHRR data, and the data was acquired by IIT Roorkee Satellite Earth Station, which has been operational since October 2002, is still running, and the nighttime data we employed. And what we see that it can create a digital elevation model at 1 kilometer resolution, and in this one we have employed a particular for comparison also, we have used USGS 1 kilometer resolution data. So the details about that one is also given. And this NOAA specifications are also given. Especially two things I would like to mention here, that the radiometric resolution, it is 10 bits data. Like in a spot or cartosat, generally you are having either 8-bit data or 6-bit data. So the radiometric resolution of NOAA is very high, and therefore you may get a better digital elevation model at that particular resolution, say at 1 kilometer resolution. So that is the advantage, because here the radiometric resolution is higher than your Landsat data and or other data. And a spatial resolution, of course, is around 1 kilometer, and rest of the things are also here for our. Now we will compare with the USGS-DM, and so that we have to register the images together so that we can see, do the comparative analysis, and then finally visual analysis and statistical analysis has also been done just to show that how close it is to USGS-DM. So these are the two digital elevation models. One is generated using NOAA AVHRR data, exploiting that inverse relationship between temperature and elevation. And this is a USGS-DM of the same area. Though this is generated using interpolation techniques, implying the contours which are available in surveyed topo sheets. But here this has been generated using NOAA nighttime data, and which is available for almost every day, and therefore you can imply such. If we see the if we start comparing this thing through a scatter plot, what we see, and this is the inverse relation which I was talking, which is also reflected in the brightness, temperature and elevation. As elevation goes, this go higher and higher, we get the less brightness temperature value, which is in Kelvin. Now we also see the comparison here with NOAA-DM for different range of elevations, and USGS-DM. So we see that it's having almost the same pattern as AVHR-DM. So two different ways the comparison was done here. Now this correlation analysis is also there, and what we see, they are highly correlated. USGS-DM and DM generated by using NOAA data 0.96. So it's a roughly 0.97 correlation has been seen between these two DMs. So you get a very good results by employing NOAA data. Similarly, Landsat thermal data can also be used at 60 meter resolution, and one can generate digital elevation model. What are the implications of that? That, as I mentioned, that Landsat ETM or OLI series data can be used. What are the limitations here? It requires the highly accurate georeferencing, because you are working at a relatively very low resolution data. So that part is very much important here. It is best applicable only in a highly rugged and natural terrain, least disturbed terrain. For hilly terrain, generating a digital elevation model has always been very difficult. But here, employing this inverse relationship, one can generate digital elevation model even using thermal infrared data, and need to have some ground values for elevation for validation purposes. And sometimes, because if we compare with USGS-DM, which is 1 kilometer resolution, so because USGS-DM might be having some seams, because between two topo sheets, if they are in two different projections, when they were joined, the seams were there inbuilt in the USGS-DM. So seams may create some problems. Otherwise, for comparison only, that problem will be there, but digital elevation models can be generated using thermal infrared data. And there are sources of DMs which I have been mentioning, from where we can get digital elevation models for our work or projects. One of the way we have already discussed is using Survey of India topo sheets or any topo sheets of any country. We have to digitize it, perform the interpolation, do some validation, ground checking, maybe through GPS data or others, and DM can be generated. So the resolution we can control here if we ourselves are generating. There are various free DMs are also available. Like example, we have just touched USGS-DM at 1 kilometer, SRTM was available at 1 kilometer, 90 meter. Now it is also available at 30 meter. There are some problems because none of these products are perfect. If I take the example of USGS 1 kilometer, so it is having the seam problem, especially for hilly terrains of Indian part of Himalaya. SRTM, if I take example of 90 meter, it is having voids. And we will see some examples. Voids means no data. Void has occurred because it is based on radar remote sensing data. And as I have mentioned, that if it is having a lot of snow or these ruggedness of Himalaya creates problems in the radar data, and therefore voids or no data values were left. So then it becomes really non-usable. But the techniques were developed and to make these data sets void free, and now those void free data are also available, or void free DMs are also available. But these voids are substituted with relatively low resolution data. So for some areas you are having a very high resolution data, but some areas though it is resampled, but original data was at low resolution. So let's see the example here at this stage, that what we are seeing, a digital elevation model of entire Himachal Pradesh at 1 kilometer resolution. The DM by USGS generated based on survey topo sheets, means using contour and then interpolation. And this is the DM of the same Himachal Pradesh at 90-meter resolution and with voids. And what we are seeing here, that these are the voids, and basically these are the no data values. Therefore, the values here are very low values which are assigned to the no data value. And if we see such DMs even at 90-meter resolution with voids, then we cannot imply such DMs for any use. But if we use this 1 kilometer resolution DM, which is void free, and these voids if we fill and get substituted by low resolution values, elevation values, then we can make a completely void free digital elevation model, and that too at 90-meter resolution. So let's see again one by one, that what we are seeing is a digital elevation model at 1 kilometer resolution without any voids, but the resolution is 1 kilometer. Whereas here we are seeing digital elevation model from SRTM at 90-meter resolution but with voids. So if we use both and fill the voids from the first one, which is at 1 kilometer resolution, that is USGS, then we can create a better product. And this is how things can be improved. So nowadays even void free digital elevation models, SRTM 90 meter and 30 meter for almost 80% of the globe are available for our uses. But the voids have been filled. Any SRTM DM which you download for your area or project area will have in some parts, if it is of hilly terrain, it will have some parts which are filled with a relatively low resolution data. So this one has to remember while using SRTM digital elevation models. There is another comparison, that USGS 1 kilometer resolution for the same area, this is SRTM 1 kilometer resolution, and this is SRTM in 90. Of course, 90 meter resolution looks much better, whereas in USGS DM you see a seam. Seam has been a big problem with USGS DM because these are based on the input data is topo sheets from where the contours have been digitized, and later on these contours have been used to interpolate the surfaces or create the digital elevation model. But seams were left here, and sometimes such data becomes unusable. But SRTM had voids problem, USGS have the seam problems, but employing some substitution techniques or some processing, you can improve the data and can create data at different resolutions. One more example of SRTM which is corrected or filled void free, but if it is, see this, the example is of Punjab area which doesn't have much hilly terrain or any other thing. So except for very little in this northeast part, you have little very small scale or hills, some simple hills are there. So the radar data didn't have any problem, and therefore the corrections are not much corrections are required, and a perfect digital elevation model at 90 meter or 30 meter can be used. These are the further different sources of DMs with different applications. At what scale you are looking, this table will give you the idea, like the application if you are for topographic mapping, different scales are available depending on your project requirements. Accordingly, different resolution data are possible. These are the sources of from where the data can be acquired, whether it is free or it will cost. That information can also be seen here. For flood modeling, what kind of mapping scale data, what kind of resolution data you require, and which are the data which will be useful, like LIDAR DSM, because LIDAR provides the digital surface information, and therefore they are DSM, and in flooding that is very helpful, and this we have also discussed earlier. So a plain or bare DM is not good for flood modeling, as DSM, which is acquired by LIDAR, will be more useful. For landslide mappings, again LIDAR DTM, digital terrain model, can be used for coastal and others, but LIDAR digital elevation models are not available free. It is very expensive technique, and also satellite based are not yet available, but rest of these are available which we can employ here. So this brings to the end of this various techniques of digital generating digital elevation models. This was the last part of this. Thank you very much.